All right, let's go ahead and talk about that first one. We're going to grade it here in just a little bit. I want to make sure you've got the basic concepts down. This was all pretty much review. Matter can be put into 4 different groups. What are the 4 groups? Solid, liquid, gas, and plasma. And as you know, you learned about these probably in elementary school, except they probably left the plasma part out because it was just a little too confusing for kids to understand. You know, they do the solid, liquid, gas in elementary school. They talk about water. And they say, of course, water in its solid state would be ice. And liquid, it's what we normally know. And in gas, it would be water vapor. And they show an ice cube and they put it on a little hot plate. And you heat it up and it now becomes liquid. And you keep heating it and it then becomes a gas. Well, these are each states of matter. You need to use that term. And what we've done to change from one state to another is we've added what? Heat. Another name for heat is thermal energy. Just a fancy word for heat, thermal energy. So as we add that thermal energy, the atoms change. They change the way they're moving. They change what they're doing. And that gets into the kinetic theory we're going to talk about here in a little bit. But first, it's about the states, okay? Now, in order to get plasma, you need extreme heat. We talked about plasma already, if you recall. In our electricity and magnetism unit, what kind of plasma were we talking about? Where was that found? When does that happen? Lightning, very good. In the case of lightning, who can tell me what happens to the air to make it plasma? How was the air changed? Zach? Good. Ionized. Now, can you tell me what that word means? When it's ionized,
like the channels of air.
the air becomes like wire. But why? What changes in the air atoms? Well, there's not positive electrons. Remember, it's only negative electrons. But you're right. The electrons are set free. Remember that normally we've got our atom with the electrons buzzing around. We've covered this already. But when we can set those electrons free, then we can have plasma. Plasma is a pretty energetic state of matter. For instance, there's a plasma cutter, a plasma torch that can cut through thick pieces of metal using that kind of energy. Yes? Can you what? Turn anything into plasma? That's a question I don't know the answer to be honest with you. I don't know. But you're going to need to change your thinking in some respects when it comes to these 4 states of matter. Because a lot of times we think that some things don't exist in those states, and they do. Like, for instance, if we're going to go from gas to liquid, we've got water vapor. We want it to turn into liquid. What do we do to that water vapor? Cool it down. And then we want to turn it into a solid. What do we do to it? Huh? Cool it down further, and it becomes frozen, right? Okay, that ladder right there, made of aluminum. Aluminum's a metal. Okay, we would say that matter is frozen. Now that kind of blows your mind, doesn't it? You don't think of that as being frozen because it's not cold. Well, cold is relative. Some of you think it's warm in here right now, and others are comfortable, right? When I say frozen, I mean I put it in the solid state. This table is frozen. Is it cold? No. But the matter has reached its freezing point. It's frozen. Some materials are liquid at room temperature that you wouldn't expect, like metals. What am I talking about? Mercury. Mercury at room temperature is a liquid. In order for it to become a solid, I have to lower the temperature even further. Okay? It has to actually be cold. Most metals don't have to be cold to be a solid, right? You see what I'm saying? So which state it's in and how much temperature, how much heat is needed depends on the type of matter. Okay. Did you find one?
Yeah, back at the shop. Is it okay to leave this stuff
Absolutely, yeah. So if it's mercury, it's going to be liquid at room temperature. If it's aluminum, it's going to be a solid at room temperature. Either way, if it's aluminum, we're going to need to add heat to turn it to a liquid. If it's mercury, we're going to need to add heat to turn it from its normal state of liquid into gas. But as you add and subtract heat, it moves from one state to another. Okay. On that assignment, you were asked to describe each of these, and we use the words definite and indefinite. Definite means we can define, we can describe the shape. It's consistent, it's unchanging, okay, is another way of using that word. Indefinite means it varies. It's not always going to be the same. So when I say shape, okay, that would be how it appears. When I say volume, I'm talking about the amount of space it takes up. We covered volume before. Okay, who can come up and fill in this table for me real quick? Taylor, give it a shot. D's and I's, put them in the right spot. It's a lot harder with the projector low, isn't it? Everybody agree with that? That's perfect. Okay, so a solid, a wooden block, for instance, has a certain shape that's always going to be predictable, and it's going to take up a certain amount of space. A liquid, even though its shape changes, if I put this pour it on the ground, it's going to be a different shape. It still takes up the same amount of space, just in a different shape. Okay, it's like taking the water and putting it in a tall, skinny flask instead of a short, fat beaker. It's going to take up the same amount of space, it's just a different shape. A gas, on the other hand, it's going to spread out to fill whatever container you happen to give it. So its shape is not always the same, it's always changing to fit that container. And as it spreads out, it's taking up more space. We can take a gas like air and we can squeeze it into a small container. When you go scuba diving, that's exactly what you do. You take a room full of air and you pack it into a small space. It takes up less space. Its shape is different, but it's still the same matter. I had a hand up back there?
Yeah.
Yes.
If you just have like a little bit of gas and you put it in a vacuum room, would it take up the entire room? Is that significant?
There are other factors like temperature. If the room were a constant temperature, it would spread out evenly to fill that room. Like if someone were to release a purple cloud of gas in here, it would spread out evenly to fill that room. Okay? That's a good question. All right. So again, as we look at the state of matter, you guys saw this simulation. We did this before. Here you see the liquid as you'd see it with your naked eye. Here you see it if you could see the individual atoms that make it up. And when it's in the liquid state, those individual atoms are just kind of sloshing about. They are moving. When we decrease the temperature, their activity slows down, and they're more huddled together, closer together. Okay? We did a little simulation in here before, if you recall. I had you guys come up and link hands. You remember this? And I put a fire underneath, and what's going to happen as we increase the temperature? Well, that's what I'm trying to show here. As I raise that temperature, you'll see little bubbles start to form. Well, what's happening is those particles are moving farther away from one another. And you keep raising it, and there's more and more activity until we reach what we call the boiling point, or vaporization. And you can see that those particles are just now, some of them are actually leaving altogether. They're going to expand. If that's not closed up, that steam expands and rises and goes out to fill whatever space, because the volume of a gas changes. It's indefinite is what we would say. Okay? All right. Now you're going to be looking at the particle and kinetic theory of matter. But before we get into that, I want to go ahead and trade these closed up. Most of you guys are done. I'm going to give you a little more time. You can finish this. You can even work on it while I'm talking here. But I wanted to show you some stuff firsthand that maybe will help clarify what you just read about. That was the particle and kinetic theory of matter. Big words, but you know what particles are, tiny little things. And you should know what the word kinetic means, because we already talked about that. Kinetic, like kinetic energy, means energy of motion. So things are moving. So I'd like someone to tell me what's going to happen when I turn on the Bunsen burner. What's going to happen here? Yes. The balloon's going to get bigger. Okay, no No big shock. You've seen this kind of thing before. But I want you to really now visualize what is happening inside there. You know, everyone says the air expands. That's true. But you need to picture that there is matter inside. Even though you can't see it and you hardly can feel the weight, there are atoms in there. The atoms are tiny little particles and they take up space. And by adding heat, thermal energy, I'm causing those atoms to move more than they normally would. What state of matter was the matter in that was in the beaker? What did it start as? What state of matter? Gas. And what is it now? Gas. I'm not going to get it to plasma with the Bunsen burner. But it is expanding from that heat. The particles are moving apart. And you know, this is actually more surprising to people than if I put water in there. And if I put water in there, they can see the changes in state. And actually, there is some water in there. Can you see the little cloud that's forming? All that swirling around smokiness you see inside, that's water vapor. Okay? And right now, it's still blown up. Why? Yeah, they're still moving faster than they were at the beginning. But eventually, as this cools down, that water vapor you saw forming a cloud there will turn back into liquid, or won't be as active, I guess would be another way of putting it. If I started with a beaker half full of water, you would have seen the water level go down, but actually all the water stayed inside that system. All it did is spread out. It got more energy from the Bunsen burner and caused it to expand. Now, this idea of adding energy by adding heat to things is real important in chemistry. It will affect how things mix. And since we can't see the atoms and we can't see their motion, we can only infer or guess, make educated guesses on their motion based on things like how quickly stuff mixes. So next time you heat up water and you're unimpressed, remember what's actually happening. Those little bubbles that are forming, the movement of the water out of the container as gas is formed, is all created by that added energy. Okay? When you heated up the water, you added energy to it. And inside now, the atoms are moving around, bouncing around a lot faster. By looking at it, you wouldn't know that this was true. Ooh, that's interesting. Hope that goes away. Okay. Still not. There we go. You got one more here. So I've got 3 test tubes, hot, room temperature, and cold. And the race begins. I'm going to add a drop of food coloring to each one. 1, 2, 3. And you can see the effect of that energy, that heat that I added to the first test tube is acting like a little stir. It's mixing things up much quicker because the actual atoms in there are moving much more rapidly, stirring and mixing in that food coloring. The room temperature one, you can see it oozing on down. Okay, the motion is faster than this one, but certainly not as fast as that. The cold one that I took out of the refrigerator, it's just now starting to make its way down. It'll take longer for that to get mixed in with the liquid. Again, what am I trying to show here? I'm trying to show you about the movement of particles. That even some things that we think don't move, like solids, there still is motion. Okay, let's back up now. The particle theory. The particle theory states that all matter is made up of particles. Go figure, huh? Atoms are made up of, or all matter is made up of atoms, these tiny little particles. And the second piece to that is not only are they made up of tiny particles, but the particles have spaces between them. They're not stuck together. Even a solid has spaces, gaps and holes and spaces in between. And even within each of the atoms, there is some space to be found. Okay? We looked at that already. If you were to break open one of these atoms, what would you find inside? What particles? Nobody remembers what goes inside an atom. Protons, neutrons, electrons. Guys, you covered that way back in elementary school. I know you covered it in 6th and 7th grade. You should know that by now. Do atoms look like little balls? No, it's just a model. And the space between the atoms when they form what we call molecules, they're much greater than that. And when we break inside the atom, it is mostly made up of what? Inside an atom is mostly, you got the protons, neutrons, electrons, but what fills the rest of the space? Nothing. Emptiness. Empty space. Okay? So an atom is mostly empty space. The kinetic theory. So we know now matter is made up of little particles, but we should also know that the particles are in constant motion. That when we go from a solid to a liquid to a gas, we haven't changed the kind of atom. It's still the same atom. Whether water is ice, liquid water, or steam, it's still the same atom. What we've done is by adding heat, thermal energy, we cause things to move more. In a gas, they're bouncing all over the place. We did our little simulation in here. I had you do that hop dance, right? Hop, 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 running all over the room, bouncing off the walls. The atoms spread out. They try to get away from one another. Just like you saw on this. What caused that balloon to stretch out? That energy from the heat caused the atoms to try to get away from each other. And as they moved away from each other, bouncing off in all directions, they expanded the balloon. When I take away that heat energy, they go back to a less active state. Okay, so these guys are jiggling around here. These guys are bouncing all over the place. And when we get to solid, even something that's solid, like this table, you wouldn't think of it as having any kind of motion with the atoms. They are moving. It's like this. It's like vibration. Okay? It's like putting someone on a very short leash. They can move a little bit, but they can't move outside of that area. That leash becomes longer when you go to a liquid and really long when you go to gas, because in gas, they can spread out and fill the container, however big that container is. So that's why the volume on a gas is what? Indefinite. It spreads out to fill the container. Liquid, it has a definite volume. It's going to fit the shape of the container, but it doesn't suddenly get more water just because you put it in a different container. Solid has a definite volume. Okay, this next slide is going to help you more with the homework. I'm going to go through this. I'm going to pass out the homework. You're going to have that and the other one I already gave you to complete at home. Who can come up and put these in the right spot? Zach? Man, I really fried myself there.
This is my hand.
Mm-hmm.
I don't know which color is which.
Well, usually on a battery, the positive connection is what color? So, with that said, okay, is that right?
Ah.
Yep, he's right, okay? We do use red to represent protons and neutrons here. Now, I went through this with you previously on another lecture, and we talked about what was wrong with this model. What's wrong with this model? How is it imperfect? Nathan? Well, they are spaced away. There is a gap in here. But the gap is actually much greater. If this were the nucleus, the electrons would be a lot farther away than I can show on this model. What else is different in the real world? They're moving extremely fast. You don't just see them sitting there. Yes. There are, in many, not all atoms, but in many atoms there are more electrons, yes. They're not circles, exactly. What else? Keep them coming, you're doing good. How about the size here? Are protons and neutrons about 2 or 3 times as big as an electron? No. The difference in size, Andrew, is huge. Okay, these would be so tiny on this particular model that you wouldn't even see them. So we draw them a lot bigger than they actually are, so that you can see, where things are. But this model has lots of problems. Again, what I wanted you to get from it is that protons and neutrons are about the same mass. Okay, same mass in here. And they're found in the center. Electrons move around the outside, spinning in what we call orbitals or shells, like planets orbiting a sun. The difference is they don't just go in one direction, they go in all different directions, different distances from that center. Protons have what charge? Neutrons have neutral. Electrons, negative. Okay? So this is review. We've covered this already. Protons and neutrons exist in the nucleus. Protons have a positive charge, neutrons have no charge. And we say they have a mass of 1. This is going to be real important down the line, so don't forget that. They both have a mass of 1. Because electrons are so tiny by comparison, we say electrons have a mass of 0. They have a teeny tiny bit of mass, but it's virtually 0. So it doesn't affect the mass of the atom. It's so tiny by comparison. So who can come fill in this table now? Brianna? You should be able to do this. In fact, this looks like a good table to put on a test or a quiz in my mind. Electrons, negative charge. Protons, positive charge. The mass of 1. Mass of 1. Good. One more. Neutrons. What's their charge?
We don't have a charge.
So give them a 0. There you go. Okay, you guys should be able to do the same thing. You should know where they're at, what their charge is, and how much mass they have. Again, this makes it look like the electron's far bigger than it is. It'd be so tiny you wouldn't even see it there. Okay, what I wanted you to understand, one of the main concepts of chemistry that I think is super cool, Sedona, is that the only difference between poop and pizza is the number of these particles and where they're located. Okay? Only difference. Well, they both start with a P. What do you want? I'm giving you 2 radically different things. One you'd like to eat, one you wouldn't like to eat. Okay? Protons, if I go from having 1, 2 to 2 protons in there, I've changed it. It's a totally different substance. It's going to look different, it's going to act different, it's going to respond to heat differently. I add a neutron, I change it to a different type of substance. As you look at this periodic table, we get into all the different flavors, different types of atoms. All we're doing is changing these protons, neutrons, and electrons. That's it. Adding, subtracting, that's it. That's all there is. All matter is made up of those 3 things. Remember, originally they said atoms were indivisible. They couldn't be divided. They're this solid chunk of something that goes into all matter. Now we know you can divide it. You can split that atom. You can take away these parts. In fact, we can manufacture some things by putting together the right protons, neutrons, and electrons. If we got really good at that, it would be like Star Trek, where you could just go over there and you could tell the computer, I'd like a cup of hot chocolate. And it would just combine the right atoms together, get them all excited, get them heated up to the right level. Boom, there's your hot chocolate. It would just take matter and it would turn it into a different kind of matter by adding and subtracting those guys. Pretty cool stuff, okay? All right, I'm going to give you your homework. You can continue working on that one now.